All right, so this video is meant to introduce you to the idea of angular momentum. And angular momentum is the rotational equivalent of linear momentum. And just like linear momentum, if we think back to linear momentum was the product of an object's mass times its velocity. And angular momentum is going to be similar in that it's going to be the product of an object's rotational mass times its rotational velocity. The symbol that we're going to use for angular momentum is L. It's not a Greek letter. It's one of the only rotational quantities that is not a Greek letter. The equation is that L is equal to our rotational equivalent of mass, which is I, moment of inertia, or rotational inertia, times angular velocity, so times omega. And the units for angular momentum are going to be the units of moment of inertia, which are kilogram meters squared, times rads per second. And oftentimes we multiply something times rads per second. The rads just kind of go away. Not sure why that is, but it seems like if you would multiply something by degree, the degree just goes away. So the overall units are kilogram meters squared per second. Now, when we talked about the idea of momentum, if you can remember, so this is just a little bit of review, you shouldn't have to copy this down, but if you remember when we first looked at the idea of momentum, we said, well, the net force acting on an object would cause my mass to accelerate. And then we did a derivation and we said, well, net force is equal to mass, and I could go back to the base definition of acceleration, which is a change in velocity over a change in time. And then, hopefully this is looking somewhat familiar, I can say this is my m delta v over time. And we ended up with this relationship that the net force times time was equal to my change in momentum. And this is where we got the idea of impulse from, where impulse was either my net force times my change times the time over which that force was acting, or impulse was equal to a change in momentum. The same can be said with torque and angular momentum. So if I go through the same idea, remember when we looked at Newton's second law revisited, we said, well, the net torque acting on an object would equal I times alpha, the rotational mass times the angular acceleration. So again, I can rewrite this because I know that alpha is just a change in angular velocity over time. So if I took this and I plugged it in there, and instead of writing the sum of my torques, I'm just going to write net torque. So if I have my net torque equal to I times my change in omega over my change in time. Again, I times omega we just learned was angular momentum. So you could also have like an impulse type of equation for angular quantities, in that my net torque times the time over which that torque is acting is equal to I change in omega, or another way to write that is that my net torque times my change in time is equal to my change in angular momentum. All right? Now, the other thing we looked at with momentum, linear momentum, was that if there were no outside forces acting on my system, then my momentum must be conserved. And that is also true with angular momentum. If there are no outside torques acting on a system, then angular momentum must be conserved. So if there are no outside torques acting on a system, then angular momentum is conserved. Which means that my L initial has to equal my L final. Or I could write it out in terms of what L actually is. So my I initial times my omega initial is equal to my I final times my omega final. And we definitely see this display of conservation of angular momentum in different things that are rotating. The classic example is the ice skater. So when the ice skater begins spinning around and they have their arms out and they're spinning around, If their arms are out, a lot more of their mass is distributed further away from their axes of rotation, so they have a bigger moment of inertia. And so that bigger moment of inertia times whatever angular velocity they have that's spinning is equal to some angular momentum. As they bring their arms in, their radius gets smaller and their mass is closer to the point of rotation. So when they bring their mass in, their moment of inertia gets smaller. And if this number gets smaller, then the angular velocity increases to compensate so that we have the same angular momentum. And we definitely see that. When they bring their arms in, they're definitely spinning a lot faster. And we will demonstrate that when we get back to class as we go through some problems. So the lecture is going to shift now to actually going through an example problem with you guys, modeling how to do conservation of angular momentum.
Okay, so this is going to be an example of conservation of angular momentum. So it says a student sits on a rotating stool while holding two 3-kilogram masses. When his arms are extended horizontally, the masses are 1 meter from the axis of rotation and rotates with an angular speed of 0.75 rads per second. The moment of inertia of the student plus stool is 3 kilogram meters squared and is assumed to be constant. The student then pulls the masses inwards to be horizontally 0.3 from the rotation of axis. What's the new angular speed of the student? So essentially you've got like a kid. Let's see if I can draw this. Holding two objects. There is the stool that can spin around. And they are spinning around at a certain angular speed. And then they bring their arms in and the question is, how is that going to change their speed? And we know from conservation of angular momentum that if my mass distribution changes as I'm rotating, that is going to result in a change in my angular velocity. So the first thing we need to look at is just the idea of what is my initial angular momentum, and then that is going to be equal to my final angular momentum. So if we recall a few equations, angular momentum is equal to a moment of inertia times the angular velocity. We're told that the moment of inertia for the student and the stool, we'll call that IS, is going to be a constant at 3 kilogram meters squared. But for my objects, my two objects here and here that are kind of hanging out, they're just acting as point masses that are rotating. And so for a point mass that is just rotating, the equation for moment of inertia is just mr squared. So let's look at my equation for my initial angular momentum. So I'm going to have the moment of inertia of my masses. So I'll call that like mass 1 plus my moment of inertia of mass 2 plus my moment of inertia of my student stool. Those are all my moment of inertias, and they're all spinning at some omega initial. And then afterwards, I still have those same objects. So in terms of symbols, it's still going to be I mass 1, I mass 2, plus I student times omega final. Except the thing that's going to be different is that these are going to be different from each other because my radius has changed. So if I go ahead and look at actually plugging in some quantities, I'm going to have, let's start off by just leaving it as variables. You should agree that the inertia of mass 1 and the inertia of mass 2 should be the same, the exact same mass, and they're held the same distance. So I'm going to simplify this and just say 2 times my mr squared plus my is times my omega initial, and on this side it's going to be same. 2 times my mr squared plus my is times my omega final. So let's go ahead and plug our values in. So I've got 2 times my mass. My masses are each 3 kilograms. My radius initial is 1 meter. And then the moment of inertia of my stool and student is 3. My omega initial is 0.75. Now over here on this side, here's where I start to see the change. My mass has not changed. There's still 3 kilograms. My radius, though, is now 0.3. We've brought them inwards. And that's the only thing that's changed. So my moment of inertia for my student and stool is still going to be 3 times my omega final. And so at this point, you should be able to go ahead and calculate out what those values are. If you want to pause the videos to calculate it to see what you get, go ahead and do that. Take a moment and do that. but we should come up with an omega final as being 1.91 rads per second. And that makes sense, because if I initially had my moment of inertia initial times my omega initial, and all of a sudden my moment of inertia got smaller because I brought my mass inwards, and anytime you bring your mass inwards, your moment of inertia gets smaller, my omega final should increase to compensate. So hopefully this gives you a good example of solving a conservation of angular momentum problem.